Right, question 10 is to do with titration. We're going to leave that. I just want to discuss this word here. Concordant. It just means in agreement. So they're saying results that are concordant are within 0.20 centimeter cubes of each other. So let's look at the gap between that and that. Right, I mean, if you get your calculator, so it's on the calculator. Right, if you did this, you'd end up with, what is it, 0.15. So them two are concordant. Now the question is, are these two which are concordant with them? So if I went from 23.10, 23.10, and to 23.15, them three are concordant. Right, now from 3.15 to that, that's not concordant because you need to add 0.25. So they are concordant. Concordant means that they're in agreement. They're within a certain amount to make them reliable. But we'll move on from that because this is more to do with apparatus. Again, here what you've got is your magnesium ribbon, dilute hydrochloric acid. There's your bung, and there's your gas syringe. So this falls under the MASH acronym. So that is a metal, which is magnesium. That is your acid, which is dilute hydrochloric acid. That is your salt that is formed, and that is your hydrogen gas. So now, if you've got hydrogen gas, we're expecting what? We're expecting bubbles. Right, and another word for that is effervescence. Right, that's to add this. All I'm going to do with this one is to plot it. We're not interested in any other part. We just want to get... So let's get this table down there. Right, so what we're going to do, you've got time in seconds, 0 time. Let's use a different color. 0 time, 0 hydrogen. So there's 1 point there. At 10 seconds, you've got 29. At 10 seconds, you have 20. That's 30 there. So be careful with this. That's 10, and so on, yeah. I'll go all the way to 80, 70, 80, and 90. Okay. So have you noticed they've got the labels on? So at 10, it's going to be 29. It's about there. So you're allowed typically half a square, so... Oh, did I put it in 20? It's not very good, is it? Let's rub that off and go back to that. Right, it's 29, and then here, where are we? Let's bring that down. So at 20 is 52. At 20 is 52. And at 30, it's 67. So you can go ahead and plot this while I'm doing this. No. Right, okay, that's near enough. At 40, 76. At 50, 81. 50, it's 81. That's about there. And then it's 84. 84 and 84. So that's like a curve. Now, if I don't mess this up, Okay, let me try to draw it. It's a curve of best fit. There you go, genius. That's it. We're not interested in anything else. Why is it not necessary? Okay. This is just a general question, so we can handle this. We can answer this. Right. The expected volume of gas produced in the first experiment was 86, and we got 84. We got right. With these sort of questions, right, one of the reasons might be some gas escapes before the bung is put on. So let's go up, have a look at this here. So what you do is you put in your acid, and then you can just drop in your magnesium ribbon, and then between you dropping in the magnesium ribbon here and putting this bung on, it might take a couple of seconds, 1 or 2 seconds, and some gas will escape out of here, right, out of this area. So that's why you might get slightly less. What other reason? So the magnesium that you put in, so for example, I want to put in that much magnesium, right? And just say, for argument's sake, it's 2 grams. Now, it might not be pure magnesium. I might have a little bit there, and a bit there. So I've weighed what I thought was 2 grams of magnesium, but really, these 3 little bits will not react with the hydrochloric acid to give hydrogen gas. So the magnesium was impure, right? So we might have had just say, I don't know, a layer of magnesium oxide, a layer of oxide on it. So I ended up weighing the oxide. Right. The student uses a graduated beaker. Graduated just means, look, you've got your beaker and it's got little marks on it to tell you how much you've put in or how much you've used. Yeah, that's graduated. Explain why it's not necessary to use a measuring cylinder in this experiment. Why? Because let's go up. Right. What they're saying is we can put in loads of this. I could have put it in up to there. It doesn't matter as long as the hydrochloric acid is in excess, which allows all this to be reacted. That's the reason. Right. Forget that. We'll move that. Right. Okay, we're done with that because that was much shorter than I thought. Because you don't want to be messing about with. I don't know. Come on. Tell you what. It's a short video, so the acid is in excess. You need extra acid to make sure all the magnesium is fully reacted, right? So a precise, accurate, really accurate measurement of acid is not needed, right? Whoa. So now the ionic equation, when you get an ionic equation, you get pluses and minuses in here, right, in the equation. And use this information use the information in this equation and the particle collision theory to explain why the rate of reaction decreases. If you go up here, if you look, this is steep. That tells you it's a quick reaction because you're getting a lot of gas in a short amount of time here. Now if you come here, look, the gas has only increased, just say for argument's sake, 6 over a time of 10 seconds. Whilst here it increased 30 in a time of 10 seconds. So the rate of reaction is going down. Now we've got a say that it's a 3 marker. Right. As the reaction goes on or proceeds, the concentration of acid, and in particular the hydrogen ions, decreases or goes down, right? This means, what does this mean? Therefore, there are less collisions, let's write that again, collisions, let's just get rid of that. Let's use the whole word and stick to that. Less successful collisions per unit time. What that's saying is something like this. Look, there's the acid, there's the metal. So at the beginning, because there's lots of these blue acids, when that hits that, you get a reaction. When that hits that, you get a reaction. Now as these disappear, there's only 2 now, so look, that might go up there, hit that, might make its way down and then hit that. That might go there, and then hit that. So it's taking more time for these two to meet up, successfully collide with the right amount of energy, and then become to complete the reaction. Anyway, we'll call it quits there. How do we stop this now?